It's a pleasure for me to be here and to speak about my science, astrophysics, high-energy astrophysics and cosmology. I was born in the middle of the Second World War in 1943 in Tashkent, a large multi-ethnic city on the former Silk Road, capital of Uzbek Soviet Socialistic Republic in the former Soviet Union. You see, it's here, it's Tashkent. And unfortunately, this was a very difficult time for the country. All resources were given to people fighting on the fronts. The civil population was semi-starving. Western part of the country, most populated, was occupied by German troops, and a lot of people and industrial factories moved from Ukraine, Western Russia, and even Poland to Tashkent. My mother and father married in October 1941, several months after the war crossed the boundaries of Soviet Union. My father was mobilized to the army in the end of 1941. He was a civil engineer and officer in the reserves. Everybody with higher technical education was an officer in the army reserve in the Soviet Union at that time. He was sent to build strategically important objects, mines, and factories in Central Asia because he did this earlier. He knew these factories. He only visited Tashkent several times for a day or two during 1942. I was born in the 1st of March 1943, and I was told by colleagues and friends of my mother much later that she had no milk when I was born, and she was spending her whole salary as a head of the pharmacy in the hospital for wounded soldiers to get 2 glasses of cow milk a day for me. I hardly remember anything about World War II because I was only 2 years old when it finished. I remember well how difficult life was in the post-war years. The long lines for bread and many beggars on the streets, often without legs or hands, but with a lot of medals and ribbons on their old military uniforms. I know that many countries had, at that time, similar situation. Several of my close friends at school lost their fathers during the war. From 1944 till 1954, my father was not permitted to return to home as mobilized officer. He was sent to work 130 kilometers from Tashkent in the semi-desert, building a dam for strategic power station required to supply with energy uranium plants not very far away. But this we knew much later. In my class of 40 children, we had representatives of at least 10 different ethnicities among hundreds populating huge territory of the Soviet Union. It was very interesting to live in this multicultural environment, together with many Russians, Ukrainians, Ashkenazi and Bukhara Jews, Armenians, Azeri, Polish, Tatar, German, Korean, Greek and Uzbek children, speaking at home their mother tongues, but coming together at the big 4-story Russian school. Many of the Jewish, Ukrainian, and Polish children moved to Tashkent during the war after the western parts of the country were occupied by German troops. Tashkent obviously has changed enormously since that time. When I was finishing school in 1960, a lot of Uzbek students were coming to study in the nearby, with our home, Technical University, Medical University, and the University of Irrigation and Agricultural Machinery. In the 70s, the new city, European part of the city, integrated with the local population even more, but I hardly know any Russians who moved to the old Uzbeki city. In 1990s, hundreds of thousands of people left Tashkent when Uzbekistan became independent, and a little earlier, mainly for Russia, Israel, USA, Germany, and Canada. It's now a completely different city than it was before. I can show you, many people are asking me why I'm Tatar in nation, in the origin, and people are asking me why my family occurred in Tashkent. I can tell you that in reality, my families of my grandparents were living here, 400 kilometers southeast from Moscow, rather close, according to the Russian, to the scales of Russia, where a lot of Tatars are living, you see here. And at some moment, my paternal grandfather family in 1930 was arrested because they were rather educated and not very poor people. They were sent to Siberia, to Shilka River, its tribute of Amur River, and here in the camp, family with children was cutting the trees. They never did this before. After a little more than a year, my elder aunt came there and exchanged her jewelry to the lives of her parents and two younger brothers, two small brothers. And they returned to Tashkent because if they will return to their place, they will be sent back. In Tashkent also was very important that people had the same language and religion. Local people. 30 years later, in 1960, I practically returned from, when I was 17, in the age of 17, I returned from Tashkent to Moscow and started my study there at the university. This is, I just wish to show you the place, the map. You see here Japan, Hokkaido, Hansu, and you see the Amur River, and this is Shilka. Somewhere here, I'm trying to find now exact location of the camp, but unfortunately nobody is alive who was there. And I remember only one thing, that two of my aunts, 12 and 14 years old, died in that camp on the Shilka River. The region in the, yes, I showed you this. This was very difficult time, not only for my family. This was rather difficult for a lot of people in Soviet Union. Several million people were arrested or were sent to exile at that time. This was time of collectivization when Stalin was trying to organize collective farm, and not everybody was keen to join them. Many people were clever enough, and we heard from previous speaker that his family left Germany before the absolutely bad time for the Jewish part of population of Germany. Many people also in Russia were leaving their cities and villages, understanding that in opposite case, their fate would be much worse. I was grown with my sister and with mother, and father was working very far. But I remember very well the day in the end of 1954, when a truck came close to our small house, and two workers brought my father on a stretcher and told me that father is unable to walk due to very strong rheumatism, and that he will now live at home and not enter the cold winter waters of the Sirdarya River, one of the two largest rivers of the Soviets and of the Central Asia. My life changed completely on that day. That very evening, before I went to sleep, father told me several stories from ancient history, and then for years I was able to ask him any question, and he always knew a simple and understandable answer or explanation. He knew very well poetry, Russian poetry, international poetry, and this was very, very interesting to speak with him. I was one of the best students at the high school, in the school, and many teachers were unhappy when I asked questions because they were unable to answer my questions. But I knew that in the evening, my father would explain these things to me. And this was some very, very special feelings that you have a person who knows so much in comparison with you, and you can believe this person and his advices. I liked very strongly at that time history, geography, and literature, and much more than any other disciplines in the school. I liked mathematics too, but it was much more interesting for me to speak with my father and school friends about history, and I had no place to study mathematics more intensively than the school program provided. But when I was 16 years old, I won several Olympiads in mathematics, and final Olympiad was the mathematical Olympiad of whole Central Asia, of Kazakhstan, future Kazakhstan, Uzbekistan, Kyrgyzstan, Tajikistan, Turkmenistan, all these countries together. And I was sent to Moscow to compete further, but in Moscow I was not, especially my solutions of problems were not too successful. But after I returned, my father told me that he strongly against any attempt on my part to study history and became a professional historian. He tried to explain to me that it is the best to become a mathematician and at the same time get an education in some kind of engineering, such as an electrical engineering, for example. In the university during first years, I also was very good in mathematics. But I am very happy that when I was invited to do mathematics, I decided not to do this. I decided to go to physics, and I'm happy what I was doing later. This is Yakov Zildovich, person whom I met in 1965, after 1 year after he returned to Moscow from also distant places in Russia, where he was working on the Russian atomic and hydrogen bomb on weaponry program. For this, he was decorated with 3 golden stars of hero of socialistic labor. I can tell you that person who had 1 star was enormously important in Soviet Union. Zildovich had 3, and among normal people, this was absolute maximum. I think that Brezhnev was first person and only person who got more. They were giving him for these weapon things. My meeting with Zildovich completely changed my life. From that time, from the time I met him to 1970, my life was full of festivity. Nearly every day he called me in the morning to my room, or I called him when I spent the night in Dolgoprudny at my university dormitory to fix a time for our meeting that day. It was, in reality, he was doing this all 25 years. We knew each other, and I was usually working very late in the night, but he was waking up very early and calling me somewhere around 8 o'clock in the morning. I remember our first meeting where he told me that he wishes to solve astrophysical problems with me. And I told him that I doesn't like to work on astrophysics because chief of our department in the university told me, Rashid, you are a clever man. Why you wish to go to astrophysics? Astrophysics is useless science. Zildovich was extremely clever. He told me, please help me with 2 small problems, and then we will return to theory of fields, to the theoretical physics. When I solved that 2 problems, I never again wanted to return to physics because I recognized how good and how great science is astrophysics. And this is then all my life was in the field of astrophysics. I became student of Yakov Zeldovich, as I told already, in the spring of 1965. Early 60s were not so interesting time in our science. Who knows astronomy, young people especially, they will be shocked if they will hear again that there was no cosmic microwave background at all. It was discovered in the middle of 60s. There were no black holes, stellar mass black holes and supermassive black holes, no quasars. All this was discovered later. No gamma ray burst. Even neutron stars, which we consider now just trivial stars, we know a lot of classes of these objects: pulsar, radio pulsars, millisecond, and accreting pulsars, X-ray bursters, and magnetars were not existing yet. Nobody was observing them. We didn't know anything about exoplanets, which are discovered now, similar to how around nearby stars. We didn't know anything about Lyman alpha clouds. It's so much came to us during these 50 years. And I really think that this was great revolution in astronomy. Maybe astronomy never had so great time as these 50 years, which after the time when I joined a group of Zeldovich. First, I wish to tell you several words about accretion onto black hole. When I came to high-energy astrophysics, people thought, and everywhere in every book, it was written that black holes are invisible because their gravitational potential is so strong that light cannot escape them. I am very happy that this person who is in the room, with Nikolai Shakura, contributed also to the present-day understanding how to make black holes visible. And main idea here is that if gas is not falling onto black hole, not radially, but it rotates because it has angular momentum. Then particles here in this layer and in this layer have different velocity, just Keplerian velocity, and they have friction. And if there is turbulent viscosity, then this viscosity helps to take away angular momentum, permits radial motion, and release of gravitational energy. As a result, whole this extended disk becomes source of energy. It is heated due to dissipation of turbulence, and it radiates a lot. And now we know that the most bright objects in the universe, these quasars, quasi-stellar radio sources, their activity is connected with accretion of matter with angular momentum onto supermassive black holes with masses of the hundreds of millions or even billions of solar masses. These are giant bodies. The effective surface area is rather small around black hole of the accretion disk. Therefore, we have a lot of radiation which is coming in X-rays, and this was the reason of my great interest to the X-ray astronomy. Excuse me. I will show you short movie how animators from NASA understand today this theory. Look to the galaxy, and in the center of the galaxy there is a black hole. And what we can see, what is occurring. You see how matter rotates around the black hole, falls there, and we have huge heating due to this turbulence, and matter is falling into the black hole, but a lot of energy is going around. To fit the most bright objects, most black holes in our universe, we need of the order of 1 mass of the Earth, whole Earth, per second. These black holes are reading every several seconds, let's say, so 1 Earth mass. This is equivalent that during the year, they are eating our sun. And we see how bright these sources, and we know now millions of these objects on the sky, supermassive black holes. And I am rather happy to show you this very rare case, not in that time when I was young, not everybody, not every physicist had his own camera. And not as today when we have even cameras in the photo cameras in the telephone. But somebody made photo of us with Nick Shakura, who is here in this room, and I am very glad that he is here. And we both were very young at that time, and we were working on the theory of disk accretion onto black holes, demonstrating that black holes are able to become very bright objects. I can tell you that we were working also with many of my colleagues. We were working on the physics of accretion onto the neutron star. You see here small neutron star. This is object with like our sun is contracted and has solid surface, but dimension only of the order of 10 kilometers here. You see, and normal star is providing gas with angular momentum. This matter falling and rotates here, and we have also a lot of energy release. But if neutron star has huge magnetic field, then all matter goes to the magnetic poles, and then radiation is pulsing. You see here the pulsing radiation, and Riccardo Giacconi and his team, I am very glad that Christine Jones and Bill Foreman, who were participating in they were first in these studies, that they were very young also at that time, but they were first people who saw this pulsation, among first people who saw these pulsations, and also occultation of the source by giant star, because this system is rotating with period 2.8 days. And it was possible to measure this period. Life is not finishing. Now I am working with several people, and I am extremely interested in the accretion in the low mass binary system, which are very old system, billions of years old, when one star, you see tiny star, is white dwarf, where all electrons are degenerate, and here is neutron star, tiny 10-kilometer radius neutron star. And again, this star is supplying matter, matter is going, rotates here, radiates an accretion disk, and is coming very close to the surface of neutron star. And you see, this is the dimension of our sun, and our sun is bigger than whole dimension of this binary system. And we are observing hundreds of such systems, and this is extremely interesting science. But for me today, most interesting is the vicinity of neutron star. There is neutron star which is like billiard ball, extremely carefully polished, with radius of the order of 10 kilometers. If I have if I will make estimates, the Mount Everest, Jamalongma, will be there only 8 millimeters height. And then matter is rotating around at a distance 10 kilometer radius, when mass of the star is of the order of one solar mass, velocity of the Keplerian velocity is of the order of half of velocity of light. And this is not particles, this is collisional flow of collisional gas. It's extremely interesting how this gas is decelerating. We are trying now to construct the theory, and this radiation-dominated plasma, when the pressure of radiation in this plasma is many hundreds and thousand times higher than pressure of ordinary matter. And this, I told you already that hundreds of such objects are observed. And I can show you the population of neutron stars, which we know now. And you can see here, this is the magnetic field on the surface from 10 in power 9 Gauss to 10 in power 15 Gauss. And this is period of rotation from 1 millisecond. We are observing objects which are rotating with period of the order of millisecond, a few milliseconds. And here you see the 1,000 seconds. I think that you see radio pulsars. These are millisecond pulsars, crab-like pulsars, very active, binary X-ray pulsars, magnetars. These are objects with huge magnetic field, 10 in power 15 Gauss. Who studied quantum electrodynamics, they know about Schwinger field. Schwinger magnetic field is smaller than value which we are observing now on the surface of these stars. I should mention that there is huge community of X-ray astronomers and high-energy astrophysicists in the world, in many countries, in USA, in Europe, in Japan, in India, in Russia, in many countries. And their spacecraft, tens of X-ray spacecraft, they helped us to discover many X-ray sources and to understand their nature. I should especially note the contribution of great Japanese series of X-ray spacecraft, starting with Hakucho. Minoru Oda told me at that time, many times, he was repeating, small is beautiful, because Americans and Russians were trying to launch huge spacecraft. And Japan was launching small spacecraft, but this spacecraft was operating very well and gave interesting signs. And there was Ginga, Tenma, Asuka, now Suzaku is flying. There is on the space station, International Space Station, there is Japanese all-sky monitor Maxi. And we all dream about the time when Astra H spacecraft will be in the sky with great X-ray colorimeters. And I can tell you that I was very happy that I met leaders of Japanese high-energy astrophysics program, and I remember meetings with Satya Hayakawa, with Minoru Oda. Unfortunately, they are not with us anymore, but I am happy to speak time to time, in reality rather often, with Yasuo Tanaka, great scientist, and I remember visits to ISAS when Hajime Inoue was director of the ISAS. I must add that here in Kyoto, you have the extremely successful X-ray experimental group, which was led for many years by Professor Kayama, and you have excellent group of theoretical people who are working in high-energy astrophysics under leadership of Professor Minishige and Kato. You have also a very strong group of cosmologists in Yukawa Institute and Kyoto University, but I think that it's already too much for my lecture to tell you about several people. I am now shifting to the discoveries in cosmology. And before I will shift, I should remind you what is the cosmological redshift, Z. If I will forget on my next slides to tell you that this is redshift, Z means redshift. If some body is, you see, radiating body is going from me, you see, receding, then spectrum which is coming to me is redshifted. When body is coming to me due to Doppler effect, which we all know, the light is blue shifted. And this was a great discovery of people, even before Hubble, who found that galaxies around us are, in reality, majority of them are recessing and not coming to us. They have redshift and Z spectra. Hubble was great that he was able to formulate the Hubble law. Hubble law is, you see, this is different galaxies. He was able to measure the distance, estimate the distance to these galaxies. And he measured also recessional velocity due to this Doppler effect. It is easy. Or, you know, it was not easy in his time, but he did this. And you see that there is a linear dependence, and when velocity of recession is higher, distance for the object is also higher. And if I have distant object, then I have very high redshift. Therefore, redshift is the way how we are measuring distance. If redshift is very high, then object is very, very far from us. Similarly, I can tell you that distance is a time in expanding universe. Therefore, along these objects which have large redshift, they were radiating long time ago. Therefore, we see very, very distant objects, and this is a definition of redshift. Observable wavelengths of the photons in the line to the emitted wavelengths. It is, we are observing now objects with redshift, for example, 7. Therefore, wavelengths emitted and observed by our telescope can differ up to 8 times. Great discovery was made in 1965, which practically changed our cosmology. This was the discovery of cosmic microwave background. It was done by Penzias and Wilson, but it was in reality predicted, the existence of such radiation was predicted by theorists. And I remember when I just came to Zeldovich, I was reading paper of Professor Hayashi about nuclear synthesis in the hot universe in very early times. Our universe is expanding today, but if we will think what was before and contract it back, then we will come. Today temperature is low, today temperature of radiation is 2.7 Kelvin, but it is increasing with redshift. And if I go to redshift, for example, tens of millions or hundreds of millions, I am coming to temperature where nuclear reactions are possible. And George Gamow, Russian scientist working in the United States, was first who in the end of 40s, recognized this and was telling that there is such radiation. Only in 1965 this radiation was discovered, and today we know that this radiation has the best black body spectrum among all celestial objects. It is just black body Planckian spectrum. There are no deviations detected yet. At the same time, this radiation is practically isotropic, and this is map of spacecraft, Wilkinson microwave spacecraft, which observed whole sky. And you see WMAP gave these discovered fluctuations. What are these fluctuations? The most bright spot, red spot here on this image, is 200 microkelvin brighter than average. Average temperature is 2.7 Kelvin, and this is microkelvins. And the most dim points, like here, which are dark blue, they have temperature below average, minus 200 microkelvin. If our universe was really so hot, then in early time we can look how it was evolving. And this is a graph which was drawn in 1969 by my mentor Zeldovich and me. And you see here the scale of masses. 1 solar mass, 100,000 solar masses, 10 million solar masses, 10 power 15 solar masses, and so on. And this is time. 1 second, 1 day, this 10 power 10, this 1,000 years, 400,000 years, and this is our time, which is 10 billion years from the beginning of the expansion of the universe. And this is a line where given mass is exactly inside horizon. And horizon is C multiplied to T, this light horizon. If there were perturbations, then before this horizon, these two universes, for example, I'm taking this and this, at this time, they didn't knew about existence of each other, and they were evolving independently. If density here, for example, was higher, there was small perturbation, then density, this universe was expanding slower than where the density was smaller. They were growing, therefore perturbations were growing, but when they crossed the horizon, then we should take into account pressure. And our radiation, which I told you about, cosmic microwave background, which was discovered only in '65, had so high pressure here, radiation pressure, that sound velocity was only twice smaller than velocity of the light. And under these circumstances, this growing perturbation started to become acoustic waves. And you see these acoustic waves, for different scales, the wavelengths of these acoustic waves is different, and they were just distributed in time. This was, everybody knew this was in the books, but when we will study the history of the universe, we will find that at the time when the universe was 400,000 years old, temperature dropped up to 3,000 Kelvin. It's twice colder than surface of our sun. At these temperatures, according to normal physics, protons and electrons should recombine and form hydrogen atoms. Before, there were many electrons here, and photons were unable to go, mean-free path of photons was very small. They were diffusing here. But after recombination, when only neutral hydrogen left, these photons were not scattered, and from here, photons were coming directly to us. Therefore, Alievich Sunyaev introduced we told that this time of recombination gives us equivalent of the last scattering surface. We hadn't introduced ourselves so beautiful term, this came later, but today this time corresponds to the last, everybody knows it as the last scattering surface. It's equivalent when you are looking, for example, from the plane onto the clouds, and cloud has boundary, and this boundary is connected, that light here is diffusing inside cloud, and here it's going directly to us. And somewhere here, photons are experiencing the last scattering, and this is the surface which we see. If there are inhomogeneities, you see this gentleman is observing these inhomogeneities of the density. The same is in the last scattering in universe. It is possible to see from we are here, it's possible to see what was occurring on this surface, and cosmic microwave background should have traces of inhomogeneities at that time. And Alievich Sunyaev made computations of this, with which phase every sound wave is coming here to this moment of when universe becomes transparent, and then it is possible to see, you see this, for example, with this phase, you have very high amplitude, and here you have zero amplitude, and so on. As a result, you should have dependence of the perturbations from the mass, or from the scale, or from the dimension of the sky. This was the prediction, and this prediction permits you to say that there are traces on the sky from these sound waves. And all what we see here, all these inhomogeneities are traces of these sound waves. And if we expand this signal from the sky map over spherical functions, we will find characteristic angular sizes. And this first acoustic peak, second acoustic peak, third, and we are observing now up to 8 acoustic peaks. Look, this was the prediction that we will see such thing. You see, and this is what is observed today on the sky. And there are several spacecraft, there are several balloon experiments which detected this, and people are happy and continue to observe. And several groups were working on this effect in the whole world. What is the result? Main result that this data also are showing us that 74% of all matter density in our universe, this is unknown dark energy. Nobody knows what is it, but it is there, and now the main goal is to study what are the properties of this dark energy. 22% is the dark matter. We don't know in the lab what is the dark matter, and a lot of physicists are working trying to understand what is it. And only 4% of matter in the universe. These are ordinary atoms, and in previous lecture you heard how complicated is chemistry and physics of these atoms, but we know a lot. Here we know a lot because we ourselves are made from these atoms. But what is this? What is this? We do not know in reality. This is how people are doing, understanding today this is time. You see, we know now the age of our universe. After start of expansion, our universe is expanding 13.7 billion years. We know this third digit with very good precision today, just because we know, we are observing this acoustic peaks. And you see, this is the last scattering surface, 380,000 years. After that, there is a time, rather long time, which we are telling dark ages, like a medieval time in Europe, where we do not have too many documents from that time, and life was very, very slow between Rome and Renaissance. Everybody of you heard about this. And then first stars appear, when age of the universe is 400 million years, galaxies, and here are we, and our spacecraft are observing today what is the universe. And this is the result in reality of that revolution which occurred during last 50 years. And a lot of people contributed to this revolution. And very important was the space, that we have spacecraft now, automatic spacecraft, which are giving us a lot of information. This is new detectors, new cryogenic, a lot of new technology, which was not available at all 50 years ago. We can go further. We are observing, I will speak now about clusters of galaxies, objects, the most massive objects which are here in our vicinity. These are clusters of galaxies, and I am showing you one of the clusters very nearby. And this is Hubble Space Telescope image. And it is great because in this cluster of galaxies, thousands of galaxies are moving. And their velocity, according to the Doppler shift of the line, is close to 1,000 kilometers per second. Gravitational potential is so high that velocity of these galaxies are huge. Then we know now, due to the X-ray observations, that there is hot intergalactic gas, and temperature of this gas is from 30 million Kelvin up to 100 million Kelvin, 10 keV. And it's very interesting that gravitational potential defined by invisible dark matter here, it changes the path of light. This is Einstein gravitational lensing. All of you heard about this, and we see this gravitational lensing everywhere. And we can, using these lenses, we can estimate what is the total mass of the cluster of galaxies, and it's still not very precise method, but people are trying now also to estimate the masses of cluster galaxies and to look for dark matter using this method. But it is extremely interesting also that these objects are well behind the cluster of galaxies, And therefore, their images are amplified twice. One, by the huge gravitational field of the cluster, and then by the biggest our telescopes like Hubble Space Telescope. These are X-ray measurements from XMM Newton. I especially took image by Dr. Churazov, who is also in the room. And you see here, dark matter mass of this coma cluster of galaxies, 10 in power 15 solar masses. Huge. When mass of the sun, 10 in power 33 grams. Therefore, this is 10 in power 48 grams. What is the mass of the cluster? Sound velocity of gas is close to velocities of galaxies. Some galaxies are moving here with supersonic velocities, some with subsonic, some having sonic velocity. And we are measuring thousands of them. And this is spacecraft. I will mention today that majority of our spacecraft have now names of great people. This spacecraft has name XMM Newton. Name is given by Isaac Newton, and everybody of you know his great contribution to science. Let's return again to CMB and return to 1966. At that time, when CMB was only discovered, but X-ray spacecraft were still absent, I came to Zeldovich and told him that there are rumors that Fritz Zwicky told that there is a lot of gas in clusters of galaxies, and maybe this gas is hot with temperature of the order of 100 million Kelvin, and then maybe it's important that somebody will detect this gas. But there were no X-ray spacecraft. Only in 1971, Uhuru spacecraft detected emission of this gas. But Zeldovich told me, look, maybe you will find some physics which will permit to find this gas. This is me at that time, and this is my mentor. And I tried very simple model that this is the motion of the photon scattered, but this, after scattering on the electron, this photon is going to me, but another photon from radiation, isotropic radiation field, will replace this photon number 1, and effect is 0. I came to Zeldovich, told him this, and Zeldovich told me this well known starting from 17th century. Till now, I don't know why it was well known, but he told me this. And then he told me, think further, and we came to following model. That if there is laser line, and this laser line is scattered on the hot electrons with temperature 50 million Kelvin. When electrons are moving with average velocity of the order of 1/7 of velocity of light, then this is the spectrum of photons which are scattered. I computed this spectrum, derived formula, and you see that right wing of the line after scattering is stronger than left wing. Photons are gaining energy from hot electrons because laser is optical light or radio light is in CMB. Electrons are very hot, therefore you are getting additional energy, and therefore photons effectively are moving to the higher frequency. If I will take now blackbody radiation for cosmic microwave, blackbody spectrum for cosmic microwave radiation, and we'll consider that this is sum of many, many lines. Each line is shifting, you see here. And as a result, I am getting this spectrum, and in relay genes part of the spectrum, in decimeters, centimeters, and millimeters, brightness of the sky should drop. And in the wind part of the spectrum, in sub-millimeters, brightness should increase. Clusters of galaxies should be, as a result, negative sources on the sky in centimeter, decimeter, and millimeter spectral bands. I should see holes in the place where there is hot gas, and positive sources were on sub-millimeters. I remember that I was giving a lot of talks about this. And usually when I was giving talk, for example, in Physical Institute in Moscow, more than 100 people, but old people after my talk were like me now, were standing and telling me, young man, I was very young, you are completely wrong. I am teaching thermodynamics for 40 years, and every my students knows that if we are observing hot gas, then brightness is increasing, and you are telling us that it is decreasing. You are wrong, and I don't like even this discuss. I was trying to explain that this is not real radiation, it's scattering and so on. And at some moment, Zeldovich was appearing in the room. When he was entering the office, he was telling, oh, Rashid is right. And then all people started immediately to say, yes, we are agreeing. And I recognized how it is important when you have heavy artillery behind you. Another thing which was very unusual for astronomers was that I discovered that this effect doesn't depend on redshift. Everywhere it should be the same. And now all astronomers thought that I am crazy, because how it is possible that all galaxies have redshift and this effect hasn't redshift at all? And solution came when John Karlstrom group in Chicago in 80s observed 28 clusters of galaxies, discovered the effect, and found, look, this cluster of galaxies at the distance, okay, light from this cluster is going to us 200 million years. And from this cluster is coming to us of the order of 8 billion years. But look, they are practically similar. No difference in the surface brightness, no difference in spectrum. This was full confirmation solution. Joel Karlstrom, he was very young at that time. He was elected as one of the youngest members of USA National Academy of Sciences due to this experimental proof. It was great, and I was very happy. He had 28 cases. These are 3 best pictures, but they are really, it's great that theory was confirmed by observations. Today, there are many specially designed instruments working on the sky. This is South Pole Telescope, just exactly in the point of South Pole. This Atacama Cosmology Telescope, 5,000 meter height. This is AMI in the rainy Cambridge. This is Zeta Ray in Owens Valley in California, from where water is going to Los Angeles. This Amoeba Taiwanese instrument on Hawaii. This Apex European telescope in the Alma site in Atacama Desert. And I can tell you that now people are observing this Zeta Ray, these 105 clusters, which are measured with redshift from 0.08 to 139 by John Karlstrom and Dan Marone in Owens Valley, with 6 tiny 3-meter dishes. And they are getting great results, which was impossible before to get when 40 years people tried, and now it became, due to the great technology, very easy. These are 3 clusters with redshift of the order of unity. These objects were born very, very long ago, and it's a surprise that it's possible to detect them. You see the telescope 10-meter South Pole, American telescope on the South Pole, this polar glow, and this is the Milky Way, our galaxy. And this is 10-meter telescope, and I tell you that I admire young people from Berkeley, Chicago, Northwestern, from tens of universities who are staying for polar night at that place. And one night there is a half a year. And they're staying when it's impossible, no connection, planes are not coming. How they're observing? This is their slide. You see here, these are galaxies, bright or star or dusty star-forming galaxies very far from us, positive sources. These are acoustic peaks. You see, these are acoustic peaks. And this is the hole on the sky where is new cluster with very hot gas. Now 1,000 clusters are detected by this way, and because effect doesn't depend on redshift, many of them are very distant clusters. There is Planck Surveyor spacecraft which continue to see this. This is WMAP spacecraft in the both Planck and Planck and WMAP are NL2 point, Lagrangian point 2 in our solar system, where Moon, Earth, and Sun are on one side of the spacecraft. And therefore, spacecraft is observing deep space, and only from this side, from one side, is heated by Sun, Earth, and Moon. When Planck is observing, I'm very glad to see every new cluster, because you see here 3 frequencies, 70 gigahertz, 100 gigahertz, 143 gigahertz. Negative effect, holes in the sky. Here you are crossing, effect should be 0 at 217 gigahertz. And Planck is observing here 0. And in submillimeters at 850 microns, you see positive source, as it was predicted by theory. And people are detecting, I told you already, more than 1,000 sources with this technique. When they find this object, they are telling to optical astronomers. And optical astronomers immediately are discovering clusters of galaxies in optical light, you see here, and you see here, again, gravitational lensing. Huge lenses which, again, this is a new source of information about our universe. These data are from Atacama Cosmology Telescope. Why we need this? Why people are spending their time and funding agencies are spending a lot of money? It's necessary just to study large-scale structure of our universe. It's necessary to check the expansion of our universe. It's necessary to know how our universe evolved. And what is most important, that these clusters of galaxies are in reality the knots in the cosmic web. And you see everywhere these are traces of sound waves, and everywhere here in the knots are clusters of galaxies. These are great objects, and we are extremely interested to see how they were appearing on the sky, when they appeared. Look here, this is how cluster was growing. No cluster at redshift 8, no cluster at redshift 5.7, at redshift 1.4, something appeared here, and near us, you see we have bright objects. This is the computations on the biggest computers in the world, but it shows the evolution, and we can predict how many clusters should be per square degree if our universe consists only of matter, just normal atoms. No clusters at redshift, practically no clusters at redshift higher than 0.3, 0.5. And we are observing now a lot of them at redshift 1 or higher using this technique. It's impossible that our universe consists only of normal matter. But if there is dark matter and dark energy, then this is the curve, and this curve is today coinciding with experiment. This is very, very important. And my last slide. I can tell you that, again, repeat you, that I became graduate student of Yakov Zeldovich in the spring of 1965. Early 60s were not so interesting time. I repeat this again. No cosmic microwave background, no black holes, no neutron stars, no gamma ray burst. You know, life was completely different and not so interesting as today. I heard from great mathematician, Vladimir Arnold, who is a really great mathematician, and he was extremely interested in the time of Isaac Newton, how the mathematics was developing at that time. He wrote several books. And he repeated me, in reality, practically every time when we had time to speak long, that before and in the times of Isaac Newton, it was easy to make discoveries because nothing was known. I do not fully believe this. I saw the Principia, book of Isaac Newton. I can tell you he was a giant, without any doubts. I admire his contribution to science. But analogy is valid. My generation of astronomers came to this world of astrophysics in absolutely right time, when a lot of discoveries were there, and they had extremely interesting life in science. Thank you very much.
ありがとうございました。それではご講演いただきましたスミャエフ博士に花束の贈呈がございます。花束贈呈。スミャエフ博士に今一度盛大な拍手をお願いいたします。ありがとうございました。